we begin by looking at the assertion that the integral from a to b of a function, f of x, integrated with respect to x, is equal to the negative of the integral from b to a. That is, if we reverse the order of integration, instead of going from a to b, we go from b to a, then we get the negative of what we would originally get. Now if we want to look at that a little bit closer, let's see exactly what that might mean. Interpreting in terms of areas, the area under a curve from a to b, if this is a function f of x versus x, I haven't labeled the axes, but is going to the integral is going to be represented by the area under the curve between a and b. So at least in this case, this integral from a to b being circled here represents the area under the curve. Now when we calculate the area under the curve, you recall that we take an average height multiplied by the width of each interval. We can either think of doing that with trapezoids, where the average height approximates the average value of the function, or doing it with upper and lower Riemann sums, where the actual average value or the integral is squeezed in between for each interval. The point, though, is that if we go from a to b, we're going to use positive intervals delta x, so that when we multiply the average height by the delta x, we're going to get positive values if the function is positive. So if we integrate from a to b, all the delta x's are positive, so if the function is positive, all the areas are positive. Whereas if we go from b to a, integrating from here to here, we're going to have to use negative dx's or delta x's, which is going to make all the areas negative. So since all the delta x's are negative, if the function itself is positive, then reversing the sign of each area gives us a negative. In any case, any time we reverse the order of integration, the delta x's reverse sign from what they were before. Since this happens to all the delta x's, then whatever integral we got when we went from a to b will be reversed, will be made the negative of whatever it was if we go from b to a. So that's essentially the reason why this equality holds. Now another equality that can be understood, at least in terms of areas, is that the integral from a to c of f of x dx plus the integral from c to b of f of x dx, that means we go from a to c and then from c to b, c being the same point both places. If we do this, we might as well just do this, just go all the way from a to b. Now that's pretty obvious if you have the interpretation of the area under the curve. If we go from a to c, we get this area. And if we go from c to b, we get this area. And if we go then from a to c and then add that to what we get from c to b, we're going to add these two areas, just giving us the area from a to b. So in a kind of a shorthand abuse of the notation here, the integral from a to c plus the integral from c to b has to equal the integral from a to b. Now of course that's an argument in terms of areas. To make the argument rigorous, we would really need to make the argument in terms of Riemann sums. Not only that, but we have the possibility that c doesn't lie between a and b, in which case the integral from a to c is all the way out to here, and then the integral from c to b reverses and comes back this way, and that should equal the integral from a to b when we add the integral from a to c to the integral from c to b. Well, one thing we can tell just by looking at the areas here, the integral from a to b is going to be the integral from a to c minus whatever this area is, which is the integral from b to c. And then since the integral from b to c is the negative of the integral from c to b, if we just replace the integral from b to c by the negative of the integral from c to b, then the negative of the negative will make this positive, and we'll see that the integral from a to b is still the integral from a to c plus the integral from b to c.